In this work, we show how to automatically tune an active 3D imaging system on the fly for the best possible performance without having a prior computational model for its light sources or its sensors. As we will see, the key idea is to put the actual system in a real-time optimization loop that runs partially in the optical domain and partially in the numerical domain. Active depth imaging systems are widely used in various applications, from industrial automation to AR and VR. In active depth imaging, and particularly multi-shot struct light triangulation, the choice of illuminations and decoding algorithms that tied to the actual system have a huge impact on the overall performance. This raises a fundamental question, given a specific set of devices. What are the optimal illuminations and decoding algorithms they should use? While existing work design patterns blend to the system and also have limited or even no optimal guarantees, we present a new computational imaging technique called optical SDD, which allows a chosen system to automatically discover its own optimal illuminations and decoding for any depth error metric. It only needs a random texture board to be placed in front of the system. Starting from random illumination and decoding, optical SDD iteratively adjusts them in real time to improve reconstruction performance. It requires no system calibration, generalized to other scenes, and outperforms the state-of-the-art by a substantial margin. Now, let's see what benefits of tuning provides compared to existing works. Unlike the existing approaches, we optimize the illumination and decoder specifically for the devices in the depth imaging system, and more importantly, we do this without any system modeling or calibration of any kind. Our approach allows the user to optimize for any desired depth error metric depending on the requirement of the application. We propose two novel decoders that use neighbor pixels information, which boosts the performance of any illumination coding. Our framework is very general. Besides common gray patterns, they can also be used to auto-tune for color system, for scenes with indirect light, and for a specific working distance. And last but not least, optical SDD provides an alternative approach to the broader problem of hardware-in-the-loop optimization of imaging systems. Now, let's see how auto-tuning works. To auto-tune a system, all the requirement is to put the system in front of a random texture board, capture its ground truth, and then run optical SDD routine. Optical SDD runs partially in the optical domain and partially in the numerical domain. We initialize from random illuminations, project them and capture images, compute errors and gradients with regard to the illumination, and update the illumination. Everything is pretty the same as a regular SDD loop, except that we compute the gradient in the optical domain. Now, let's look at how optical SDD works in action. Consider a struct light system composed of a consumer LG projector and an industrial IDS camera. Now, let's use optical SDD to optimize 4 illumination patterns for zero tolerance error canopy, which means that we want to maximize the number of zero error pixels. So here, we show the evolution of patterns and the objective function in the training process. For each iteration, top left shows 2D projection pattern, top right shows their 1D profile, bottom right shows objective function and reconstruction error for the training scene, and finally, bottom left shows the confusion matrix, which measures how two projector columns are confused with each other. As the training continues, patterns start developing meaningful structure in response to system-specific properties. Here, we show how pattern evolution influences reconstruction of the training scene on the top right. In the middle, you see the disparity map of only zero error pixels, which get denser and denser. It means we successfully reconstruct more and more number of zero error pixels. And then, to see how it generalizes to unseen objects, we test the patterns at each iteration on a challenging scene shown on the top, which contains high-frequency geometry and very low albedo regions. Again, in the middle, you see the disparity map for 0 error pixel, and on the bottom, you see the reconstructed error for the training scene and testing scene. Finally, let's go over a few selected experimental results. First, let's see how change of the camera project system changes optimal illuminations. Here is the LGRDS system that we just used for seeing the evolution of patterns. Now, let's keep everything fixed and only change the projector to a laser one, picopro in this case, which does not have any lens. Thus, we found that the optimal patterns for laser projector have higher frequency content, which reflects the laser projector property. Now, let's apply the optical STD on a color system. Here we use a smartphone camera and 4K color projector, and on the right, you see the optimized pattern color illuminations. We also use optical STD to auto-tune a computational camera for one-shot structure light. Here we use a recently developed two-bucket camera called C2B and a DMD projector, and auto-tune for one tolerance, which optimizes the number of pixels with error less than 1. Although the camera has built-in black box post-processing pipeline, we can still optimize the patterns specifically for that without requiring any modeling. Here we show the optimal illuminations performed in live 3D reconstruction of a dynamic scene. Please note that the noise regions are due to sensor noise and not from the patterns. We also optimize this system with a L1 penalty, which minimizes the mean disparity error. As you can see, changing the penalty totally changes the structure of optimal pattern. And here is their performance in live 3D reconstruction of a dynamic scene. While the disparity is smoother for L1, the disparity map for one tolerance pattern contains more accurate pixels. And lastly, we show how it performs in comparison to the state-of-the-art on another testing scene. Let's use LGRDS system to optimize for zero tolerance and also L1 penalty. We show the disparity map of only 0 error pixels for 0 tolerance patterns overlaid with percentage of 0 error pixels. And we show the disparity error map for L1 pattern overlaid with its mean disparity error. We want to draw your attention to the scene used here. It runs on a very dark scene that contains many variant geometries, like the pine cone on the bottom, and yet more than 70% of pixels are reconstructed without any error. We then compare each with the state-of-the-art algorithm. First is the pattern auto-tuned with 0 tolerance, and then for patterns auto-tuned with L1 tolerance. In both cases, auto-tuned patterns outperform the existing work by a huge margin, almost by 100% in both cases. It is worth mentioning again that our patterns and decoder work with uncalibrated systems, while the existing work require radiometric calibration. And finally, we test the performance of indirect light. We first try patterns and decoder tuned on the board and find it performs weak for the scene with noticeable indirect light. This is not surprising because the board does not have any indirect light. Next, we change the training scene to the object with noticeable indirect light transport, and we can auto-tune patterns that are far more robust to the indirect light scenes, and also it outperforms the state-of-the-art. More details and demos can be found in our webpage. Thank you for your attention.